So I think I need to make sure, so keep your finger on 19, of course. We talked about a whole bunch of terms. We talked about risk, portfolios, different types of investments. How should the risk factor change as you get older, right? What should your portfolio look like? What is a portfolio? A portfolio is like a folder with a bunch of investments in there. Then we started to talk about simple interest. And note that simple interest, most of the time it will say simple interest, but if it doesn't, the key to look for is if it doesn't have any compounding periods, you're definitely in simple interest territory. I'm going to tell you this, most of this unit is not going to have to do with simple interest. Most of what we're going to do once we switch gears, some of you might even forget about it. I just don't want you to forget about it. Okay, so every once in a while it does creep up. Just make sure you have your formulas and you know that time is always in years, right? And that you have two options there to choose from. You can use this formula here, or you may use this one if you have two unknowns in I equals party, right? If your party ain't working, maybe try this one, okay? And this one right here, this concept is true. This is on page 9 in case you're wanting to follow along. This is always true, guys. Once you know principal and how much interest you've earned, once you know those two things, adding them up gives you the future value, like the amount that you will have in the future. At the same time, if you know interest and you know how much you have in the future, you can subtract, right? You can go A minus I will give you P, right? So this concept is always true, and it will get you out of tough situations sometimes if you feel like you don't have enough information. Then we did a rate of return, and there are variations of this formula. So one way could be to say, take the future value, subtract the principal from it. So this is A minus P gives you I, right, guys? Future value minus how much you put in, that's the interest you've earned. So it's essentially interest divided by the principal times 100, or you can just think of it interest earned, or the earnings you've accumulated divided by the amount deposited or invested times 100. So they're the same thing, they're doing the same thing, but sometimes one is better to use than another one, okay? We did a bunch of math to a bunch of examples, and then we transitioned over also this on page 13. Sorry, it's a little bit, I'm jumping, I know, but technically this is already supposed to be down. So on page 13, we did one of those just flat out investments, and we had to figure out, like, this is basically our gain here is the interest that we've earned. Okay, so we added up all of our gains, divided it by all the money we've deposited, and we came up with 4.17. Can a rate of return be negative? Yes, rate of return may be negative, and it may be more than 100%, right? So this just gets me to think of, maybe I'm going to go back to rate of return here on page 9. And I will just say this. At the bottom of 9, rate of return may be greater than 100%. So example, you could have 500%, 317.18%. It could be a big number. And rate of return may be negative if loss incurred. If you experienced loss, right, in your investment, then the rate of return would be negative. All right, so we've got that. If you're not sure about if loss, and Kurt just says, tell yourself if you lost money. If you lost money, it's negative. I have never seen a negative rate of return on an exam, but you never know what they're up to, right? So maybe I will make that a point to bring it up somewhere on an AC so that if it happens, that we are comfortable with that. We shouldn't be comfortable with loss, but it happens. Keep going, keep going. Then we talked about, on page 16, we talked about compound interest. That is, most of the investments in a bank are compounded, okay? Unfortunately, when it comes to savings, it's compounded yearly. What's yearly? Once a year. When you owe money, for some reason, it tends to be daily, right, or monthly. So, not always. You have to look around, okay? And we talked about the differences between simple and compound. Simple is linear. Compound is exponential. Is exponential always better? Not necessarily, right? You would have to kind of graph it or maybe do the math, like in the future, which one will hold more money in the account at the end of the day. That's where you land, okay? Keep going. We went to page 18, and we talked about the rule of 72. So this is just an estimation tool, and if a question says use the rule of 72, then you must use the rule of 72. So the time for something to double, for your investment to double, is simply found by going 72 divided by the interest rate. It stays as a percent, do not convert into a decimal, and it is essentially the doubling time. Most popular is this one. But sometimes you can also be asked, what interest rate do you need to double your money in a certain time frame? So let's say you're looking at doubling your investment in 10 years, right? Then you would go 72 divided by 10, that's 7.2. You need an interest rate of 7.2% if you want to double your money in 10 years, okay? And I showed you an example of a mix of figuring out the doubling time and then using it to estimate how much money you would have way down the road, okay? So this question, right, gave me enough to figure out the doubling time, which was 26.18 years. So I started with $2,000, I double it in 26.18 years. Another 26.18 years go by, I double my money again. So you will have about $8,000 in 52.36 years. Okay, so that's something you can use your doubling time and take it even further. Okay, just like exponential functions. All right, let's go to 19. Heiko would like to invest at a rate of 2.35% compounded weekly. There's that key word. That means that letter N is going to be 52. Compounded weekly means 52 times in a year. Using the rule of 72, estimate how long it would take for the investment to double. Explain your answer. So, rule of 72 calls for time is 72 divided by the interest rate. So we go 72 divided by 2.35. And you get 30.64 years. That's it. If that's all the question would ask, you're done there. Expand. I like to use this opportunity to expand it, right? So what does that mean? Time and money. At the very beginning, you've got 6,000. 30.64 years go by. Your 6,000 will have doubled. I have to say we're making an assumption here. We're making an assumption that you've made no further payments on top of that, okay, guys? You're just letting it sit in the bank, and it's just earning interest, earning interest, earning interest. You're not coming every year and saying, oh, put another 1,000 in there, put another 500 in there. You're not touching it, okay? This is just sitting. Another 30.64 years go by. That is 61.28, right? You basically go plus 30.64. Your money will have doubled again. So you can use this reasoning to figure out how much money will you have past that one doubling rate, doubling time. And so we can just go dot, 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 dot. So basically over here, you're doubling. Over on the left side, we always add our time, okay? And again, it's an estimation tool, okay? We're good? Right. So, I don't know, I feel like I love you having certain tools that don't require a calculator. So let's say you look around, oh, there's an interest rate of 7% right there. Somewhere on the poster, right? And you're like, oh, I wonder how long that would take, right? And you go 72 divided by 7%, that's about 10 years, right? About 10 years, that your money doubles. So if you have $2,000, in 10 years you'll have 4. Another 10 years you'll have 8. Another 10 years you'll have 16, right? So you can do some quick math like, oh wow, it's not bad, right? So it grows faster, you can actually see it. Use your answer in A and the compound interest formula to verify. Let's verify what we just found. So this is the compound interest formula. Notice that compounding had nothing to do with my rule of 72. It wasn't used once. All you need is the interest rate. So let's verify. Principal is $6,000. 1 plus interest rate is 2.35. Sorry, 2.35. So it's this divided by what goes down here? 52 to the power of 52 times. What is our time that we're going to test this with? 30.64. Yeah. I'm going to make an, if you like arrows, you're going to like this one. Okay? So I'm using that time. Supposedly, I will have $12,000 after this many years, right? So let's do the math. Let's clean this mess up here. What a mess, right? So I go 0.0235. I should say this, okay? I want you to be careful. Don't lose silly marks. If you need to figure out what 2.35% is as a decimal, you go 2.35 divided by 100. That's what I get there. You divide that by 52. You hit enter. going to be a very small number. Then you go plus 1. Like I actually work towards the front. So that's what I have inside the bracket. Do not round, okay? And the power, the exponent is 52 times 30.64. Which is 1,593.28. And here's where you could enter everything at one shot here. So watch this. I go 6,000 times, I copy paste that number into here, this one, to the power of, I copy paste the exponent in there. So you go up, arrow, hit enter, it brings it in there. So you have 12,325 and 9 cents. Is this accurate? Yeah. It is accurate, right? We have a bit more, but remember, it's an estimation tool. So we are fairly close to what it should be. Check, right? Double of $6,000. Okay, so we're good. Oops, sorry. Verify this by calculating the doubling time using your knowledge of exponential functions. You had to do that, Mr. Erickson, right? You had to bring exponential functions in here. You couldn't just leave it, right? Watch what I will do here. I will let y1 be, look at where my finger is pointing right now, in this row right here. I'm going to copy everything except for time. I'm going to leave that as x. So 6,000. We can cheat a little bit, right? It's whatever is inside the bracket ended up being this here. 1.000451 and something to the power of 52x. Is this an exponential function? Yes. How do you know? X is in the exponent. Okay. How did I do doubling time when we did when I gave you exponential functions? What did we do to figure out the doubling time? y2 is equal to, how much do we start off with? 6,000, right? What's double that? 12,000. I'm going to show you times 2. And then we're going to go second, trace, intersect. And we better get x being close to the 30-year mark, because that's what we're expecting. So you grab your calculator. 6,000. 1.000451. Let's just do that. Let's stop at 451. It keeps going, but that's fine. To the power of 52x. And then hit graph. Let's see what happens. I see something. Do you guys see? You probably don't. Let's try zoom 6, all of us. Let's go to the center, right, to the origin. And then try zoom fit. But we know this starts at 6,000 along the y-axis and then goes up, right? But let's see if this does the trick for us. Hey, I see some. So I just need to see more this way. So x max, what do you think? Because x represents my number of years. What do you think we should put in there? 50? 60? Y min, I don't like it to be in the positive, so I'm going to go y min is like -10. Y max, if I start at 6,000 and I keep going up, I should probably go 15,000 or 20,000 and the Y max. Let's try 15,000. Hit graph. Okay, that's what I see. Let's draw a line y2 is equal to 12,000 now. So you go to y equals, hit graph, voila. Second trace 5, enter, enter, enter. What do I get? 29.56 years. Almost 30.64. Not quite, but close enough, because it's an estimation tool, right? Some of you might wonder what's happening here. So I will just do this for you here. And this is our 12,000. Right, so I basically found that intersection between 12,000 and my exponential function. I'm going to ask you to try. To be honest, this was a bit of an exploration. This was just like trying to get you to see how's everything connected. How's everything that we're doing connected? Because I told you compound interest is exponential, right? So that's why I went into this here. And we know how to do our compound interest calculations, so we figured it out there. And we learned about the rule of 72. Okay, so everything is connected, right? It's not just like I'm making this up. It's actually something that we use to estimate. Okay, thank you. Can I ask you to go to 26? And try that real quick. So I'll do one with you because I know it's still early in the game here. Page 26, it says to use the rule of 72. You cannot escape that. To estimate the amount of time required for the investment to grow to the goal stated. So you want a $1,000 investment to grow to $8,000 using 8% interest compounded annually. So, time for doubling is 72 divided by 8. What's 72 divided by 8? 9, right? 9 years. You found the doubling time of your investment at this interest rate. Because remember, the amount of money you have has nothing to do with it. You could start with $1, and then you want to know how long it's taking you to have $8. This is independent from this part. So you first have to do this. This is your doubling time. Okay? Every 9 years, your money is going to double. So let's go back here and make our table. Time and money. You start at time 0. You have $1,000. Let's do this here. We want to get to what? 8,000? So we need to double once to get to 2,000, right? We need to double one more time to get to 4,000. We need to double one more time to get to 8,000. That's our goal. So how many years will it take you to get there? It will take you 9 years to get to here. It will take you another 9 years to get to 4,000. and it will take you another 9 years to get to 28,000. So what happened on this side? I went plus 9, plus 9, plus 9. Okay, 9 times. So it will take 27 years. Okay. Can you try these ones real quick? And then I'll move on to our next section here. What did I assign? 22 to 26, so this one was assigned? Oh, I thought I hadn't assigned this far. Well, I'll give you some time to do it if you haven't done it.